So for today, I'm going to talk a little bit further into our design standards and what that actually means for us. Um, so just to start off, this is where we kind of left off. We talked about what other high school programs kind of use as their design standards. We talked about what RoboCup robots use, and then we talked about what things we have. And that's kind of just a circular thing where we can keep talking about this over and over again. But we kind of want to do a hybrid between these two. We are in RoboCup, so we should probably try to follow what they do, but we also have the tools more applicable to what teams in this type of program do. Colleges have a lot of cool tools that we don't necessarily have. So their robots are definitely much fancier looking than ours probably will ever be, unless we talk to like outside manufacturing labs. But I do want to be able to build the skills of the things that we do in here. So let's try to build off of whatever strengths we have. So just to move forward, the next few slides are going to be talking about standardizing of what other RoboCup teams do and how that kind of applies to us. So for tubing, uh, most of the time they use tubing for mechanical specific things. So they're very, very much focused on the arm pieces and things like that. Whereas for the flat plates, that's their primary structure. So basically their entire uh, robot is housed around and inside of flat plates that are connected together. Maybe there is tubing on the inside of that, but for the most part, it's flat plate, aluminum or plywood, and then just doing a comparison of what we do right now. Not saying this is bad. I think this is great for prototyping. We got a robot working really quickly because we had tools and equipment that was really easy to work with. So this is valuable for the prototyping phase, but we can transition from this to this really quickly. And then for the overall design of what we do, again, open top test bench, that's great for prototyping. That got us a solution really quick. But as we transition in, think more 3D than just a flat plane that you put things on top of. Think about how it's enclosed, how is it safe, because this challenge realistically is going into disaster situations. So if we went into a disaster situation with stuff on top like this, debris is probably going to fall and hit this versus their stuff is all enclosed. You could argue that that might catch on fire because it's just wood. But think about what this application actually is, and that should help lead us into how we're going to design things. So for us specifically, the power methods I think is one of the things that we can try to standardize on. We've already started doing this on the ARM, so ARM team is doing a good job there. But there are, things for power delivery and for power transfer. The worm gear motors that we use, the power delivery is the motor itself. The power transfer is the gearbox to the output shaft. In FRC use and other high school robotics, the motor is separate from the power delivery, which is the motor, is separate from your power transfer to allow for higher customization. This seems more appropriate to me, one, because it's my background, I've done this for 20 years, and two, we don't quite know the actual perfect gearbox yet, so that might be way overpowered for what we need. So if we can actually key in and do some designing to understand what gearbox we need, we can do power delivery where we stack a bunch of these planetaries to get the right ratio, like the ARM is doing, or we can gear it out or sprocket it out to get from where the power delivery is to where we want to transfer the power. So that's why I'm showing, this is a great example photo that Vexpro has on their website for all the methods of power delivery and power transfer. And then when you think about fasteners, you have to think about what we're building around. So if we are using 80-20 everywhere still, even into the future, if we're using 80-20 as one of our primary structures, we should probably use quarter 20s, at least in anywhere that we're interacting with 80-20. Anywhere we're not interacting with 80-20, we should use either 3/8 rivets or 1032 bolts. The reason why you can use one or the other is that's basically the same hole size you need to drill out. So when we're machining, we can drill out the same hole size and it'll fit either a 3/8 rivet or a 1032 fastener. So it makes it easy. A lot of the FRC stuff that you see here also uses 1032s as well. So that helps standardize a lot of the things, whether or not you use bolts, so fasteners for when you want to be able to take it apart, or you use rivets if you think that that's going to be a more permanent part of your solution. You don't. So these are blind rivets, which means when you rivet them on, it mushrooms the back and it just compresses together. So it doesn't need a nut. So that's also another thing. So correct. Yeah. So if we're not doing, so if it's box tubing like you see here, this is 2x1 box, this is 1x1 box, and you might not be able to get inside the tube really far, then you use the rivets instead of fasteners. This is an example of a buddy of mine from Hawaii. He actually runs a educational makerspace lab, kind of like what we have here, hopefully in the future. Um, and we can do and make something that looks this good, right? All he does is he cuts out flat aluminum plate, which we can do on our router, and he cuts straight cuts on the ends of 80/20 on a bandsaw. He's got a nicer bandsaw than we have, but that's easy to find. And the only thing that's missing, I think, from us to get here, I think you guys are clever enough to do this. I think it just takes a little bit more training in actual mechanical design. So this is also the same team. So this is the last slide you saw was how they do products. They actually do products for their community, and the roof rack was one of those things. This is what the robots look like. We can make a robot as complex looking as this, because if you actually boil it down to what their physical mechanical design standards are, as fancy as these shapes are, that's a flat plate connected to straight cut box aluminum. And you can just translate box aluminum to 80/20 like us, right? They're using all the same components and cutting with the same tools that we currently have in the shop. We just need to get more familiar with the mechanical design to get to this point. So for any of you guys doing mechanical design, and if this seems like a too big of a gap from what you know now to what you want to get to here, let me know, and I can actually sit down and do like design CAD lessons on how to design robots, because that's just my background. Okay, so this is our next steps. I do want this to be a conversation between all of you in your E4 classes. Talk about what these should look like. So what are we going to use for primary structure? I've got examples, and I've got what I think we should use, but I also want to hear if you guys have anything that I might not have thought of. So primary structure, is that 80/20? Is that 1/4 inch or 3/8 aluminum? Is that 1/2 inch polycarbonate that's routed out to make fancy patterns? And then smaller connecting structure, is that 1/8 inch aluminum? Is that 090 aluminum or polycarbonate? We use acrylic a lot, but that's obviously really brittle, and in the real world, that's probably not going to be useful for what we need. And then determining fasteners. So do we use 1/4 20, 3/8 rivets, and 1032 bolts? If that's not what we want to use, and if there's a good reason why we should use something else as a standard, we should come up with that now. Because once we have all these things, I'm just going to buy fasteners and materials of the sizes that we determine. That way, it's just always stocked. That way, it's never an issue of, well, I want to build with this, but we don't have that resource. I just want to stock it. So we'll have all the nuts and bolts of every length and size that we want to standardize around, just so it's not an issue. Like I need to buy 10 bolts because we didn't have it before. Like that slowed down your project for like a week because we were just waiting on bolts. So if we know what we're going to design around and we always design to that standard, then we don't have to wait for anything. So this speeds up our process a lot. So next week, hopefully, well, not next week because it's going to be a short week. The week after, we'll do some more mechanical design practices and talk about, I'll show more specific robot components and how those translate from looking at a robot and thinking it's just a complex shape to boiling it down to its most simple parts that actually makes sense to you as a part of a robot. So that's all I had. Is there any questions or any suggestions right away of what you think material standards we should be using for RoboCup or other projects if you're doing other projects? What have you guys been using primarily for the ARM stuff that you're designing right now?
The milled aluminum and the 80/20.
Yeah, exactly. So we're already starting that standard here. So if we can implement that and make sure that's adopted across the board, that would be really helpful.
And then for like the rocker buggy system, that's milled aluminum and 80/20.
Yeah.
And then for the base, we can make the frame out of 80/20.
Yep.
What that board's gonna be.
Yeah, I think our biggest disconnect right now is just understanding how to turn that flat board on top into an actual enclosure, right? And I think it's just turning it into more 3D design and understanding how to design for structure instead of designing for a flat plane. So I think once we get past that step, a lot of our other design stuff that we're doing is going to skyrocket really quickly. Hopefully having like a much, I want to basically redesign that entire rocker bogie using that concept, but making it look like the fancy robot that we saw, right?
I think for like the legs, since the rocker boogie is like a completely different system than like any other RoboCup, we could use 80/20. But then for the actual like structure of where the box would be, that would like cover all the electronics. Do you think box aluminum would be better since it's lighter?
I think we can do box aluminum, but I also think, can I go backwards on the screen? That's lame. I think we can design, like, if our chassis was thick aluminum on the outsides, and then 80/20 to cross brace it, I think that's a really attractive way to do it, right? Because we're used to making flat parts, and we have a big CNC router. We should just make really fancy side panels for a chassis, and then have the 80/20 cross beams, and then have polycarbonate or whatever, or even just plywood on the bottom. That way we house all of our electronics inside of that. That's essentially what these robots do, right? Like they've got, picture that as our flat aluminum plates, and then I'm sure in the corners or something they just have metal to keep it in, which could be our 80/20. So we could take these as inspiration and figure out how to modify what they're doing to do what we need to do. Like I said, my motto is steal from the best, invent the rest. I hate starting from scratch. If we know that this has been existing for years, we shouldn't have to do it ourselves. All right.
I have a question.
Yeah.
So are we planning on just like adding on to our current chassis, or are we just trying to kind of like restart?
I think it would be really valuable if we could make modifications that we can swap in and out of what we're working on right now.
Okay.
So it's up to you guys though. If you want to start from scratch and have basically keep this together and then make it basically a new one, and then start porting the functional components over to that new one, then that works too. So it's whatever you guys want to do. I just want to have something that we can start working on and making a evolution of design like next week or after Thanksgiving. I think that'd be really valuable.
And then for that cover, like I think the challenge is the arm. We haven't finished.
Yep.
Just making that mounting hole.
Yeah.
So like I get that. Or we cut it out of aluminum and then bend it over so we can make it like a dome.
So having a cover makes it actually easier for you guys to not have your final solution ready to go, right? Like this is the top plate that they're using to mount their arm, but everything else below that, it doesn't matter, right? So we can make the entire housing of the chassis to house all the electronics without even making that top cover, and that top cover just gets modified for whatever we're putting on the arm. So we can design the rest of the chassis without even thinking about how it connects to the turret. So that.
What I'm asking though is, do you want us to make an aluminum cover and then bend it over?
I think because of our strengths aren't bent aluminum, our strengths are more straight aluminum, and then figuring out how to connect those corners together. We should probably like have 80/20 rails that run across the top and the whoa. Oh, you can go backwards. Whoa. The top and bottom, connecting the top and bottom parts of the aluminum or polycarbonate that we're going to use as the side shells. So we can design around it and just keep the top part vague and allow for us to put that turret on essentially. Yeah. Any other questions? Even general design if we're not doing RoboCup design. Yeah, I mean, if we have the ability, to basically put anything on that top plate if we can design a housing around it first. I wouldn't recommend a Nerf gun or anything that's considered a weapon.
We don't use the G word. We use a Nerf projectile. We gotta get
All right.
We spray painted black though.
Anything else? Any other questions? We only got 4 minutes left. Okay, so E4 students as a group in your class periods, please try to make a list of what you think our structural standards are and our fastener standards are. And then next Monday's meeting, let's talk about what those should be, and we'll just purchase what we need and have those stocked and ready to go so we can design around what we know we're going to use.
So like talk